Hey guys, Mr. Backwork here. In this video, we're going to take a look at Leibniz notation and antiderivatives. Now, as we're writing things out, that dx might seem kind of inconsequential or even unnecessary when we're using it in the indefinite integral, where it's the integral of f of x dx, as we're representing the general antiderivative of our function f. But it's incredibly useful when we look at the effects of the chain rule when we've got function composition involved. So in this example, we're going to let f of x be the function x cubed plus 1, and we're going to let u represent x squared. And what we're going to be doing is finding some different antiderivatives using these two pieces of information. So for part A here, we're just going to find the antiderivative of f of x dx. So we're really looking at doing the integral of this x cubed plus 1 dx, since x cubed plus 1 is our f of x function. So with that x cubed, if we use the anti-power rule there, then I'll take that x cubed, I'll add 1 to the power, and then I'll divide by that number. And then with that 1, anytime you have a constant that you're integrating or anti-differentiating, you attach an x variable to it. So that becomes 1x, but we don't really need to keep the 1 in front, so we can just call it x. But then anytime we're doing an indefinite integral, we have to remember to put our plus c constant value on the back end. Now in this part, slightly different. We're not doing the integral of f of x dx. Now we're doing the integral of f of u du. So what this means is that we have to take that u and plug it into our function where the x is. So we're going to be doing the integral of, replace the x with a u, so this will be u cubed plus 1, and then this is du. Well, now if we integrate this using that anti-power rule, I'm going to take that u, add 1 to the power, and divide by that number. And then similarly with this 1, when you integrate a constant, you have to attach the variable. This time our variable is a u, so this is going to become 1u. And then we throw our plus c on the back end. But then there's one extra thing that we need to do, because our directions say that we want the antiderivatives to be in terms of x. So we need to take the u that's in here, and we know that u is equal to x squared. So anywhere we see u in our antiderivative, we're going to replace it with x squared. So this becomes x squared to the 4th power over 4 plus x squared plus c. Well, if we take x squared and raise it to the 4th power, that becomes x to the 8th over 4 plus x squared plus c. So there's our antiderivative written in terms of x. Now this last one, we're going to do the integral of f of u dx. So what we're going to do first is take u and plug it into this f of x function. Get rid of the x, replace it with a u. So this is going to be the integral of u cubed plus 1, but then on the back end we've got dx. Now on the previous example, we were allowed to do the integral or the antiderivative right away because the variable in the function matched the differential on the end. Well, here we've got a u in our function, but an x differential. So before we're able to do the antiderivative, we have to do the substitution. We need to get rid of that u that's in there and replace it with what we know u is equal to. So this is really going to be the integral of x squared cubed plus 1 dx. And now that our variable matches the differential, now we're able to do the actual antiderivative. Before we get to actually doing the antiderivative, though, I'm going to clean up this power in here. So if we have x squared and we cube that, that becomes x to the 6th plus 1 dx. And now we'll finally do that antiderivative. So take that x, add 1 to the power, and then divide by that number. And then here we're attaching an x to that 1, but then we have to put our plus c on the back end. So when we're doing our antiderivatives, we need to make sure that the variable in the function that we're integrating matches up with the differential on the end. That's going to be it for this video. Thanks for watching.